This is the static field meter FMX-003 that was donated to the channel by Nutri. The meter also comes with an instruction manual, grounding clip, and a case for storage where the meter is not in use. It also ships with a 9-volt manganese battery. This battery chemistry was selected as it won't leak like alkaline batteries do. The unit can operate with alkaline batteries, however, it is not recommended by the manufacturer. I have had various pieces of equipment damaged by leaking alkaline batteries. Static electricity, commonly experienced as a shock when touching a metal object after walking across a carpet, is precisely the type of energy measured by this meter. Not only will it quantify the strength of the static charge, but also determines its polarity, distinguishing between positive and negative charges. I have a science kit for exploring static charges. It comes with 3 rods made from different materials: glass, acrylic, and ebonite. That's a material made of hardened rubber. And 3 different types of cloths: silk, wool, and cotton. The science kit suggests trying different combinations of rubbing the rods with the various cloths and seeing the results. I found the best results are from wool and ebonite and cotton and acrylic. A classic classroom science experiment that demonstrates the presence of a static electric charge goes like this. First, I'll show the ebonite rod is neutrally charged and cannot pick up these bits of paper. Next, I'll induce a static charge on the ebonite rod by rubbing it with a wool cloth. And finally, the rod is attracting the paper bits. I will perform the same experiment with the acrylic rod and the cotton cloth. The science kit is missing the ability to measure the polarity and quantity of the charge. Even though the results appear to be the same, the charges are, in fact, opposites. Let's bring in the meter to this experiment to measure the charges on these rods. To operate the meter, first turn it on via the power switch. The LCD display will come on. At the top of the display, there's an analog scale. In the middle is a 3-digit display with positive and negative polarity. At the bottom left is the battery level, and the bottom right is the scale, in this case kV, which stands for kilovolts. If you listen carefully, you'll hear a faint humming. That is normal. The sensor must be positioned 1 inch from the surface to give an accurate reading. The 2 red LEDs in the front of the unit are used to measure the distance to the surface. When the 2 LEDs converge and become one image, this is the appropriate distance of 1 inch. I'll start with the ebonite rod and wool cloth to charge it up with static electricity. As I begin approaching the sensor, it detects about -1 kV. The analog meter at the top shows a lot of bars on the negative side. This is because the meter is in the low range of plus or minus 1.5 kV. But the meter switches over to the high range when it exceeds that. The high range is plus or minus 22 kV. The ebonite rod seems to measure around -6.5 kV. But notice if I get the rod closer than 1 inch, it will show over -8 kV. For accurate and consistent readings, it is important to keep the meter 1 inch from the surface. Next, I'll charge up the acrylic rod with the cotton cloth. This time the static charge is positive. The bars on the top are on the positive side of the meter. It's hard for me to estimate the distance, but I can see at one point it was reading consistently at plus 6.5 kV, roughly the same voltage but the opposite polarity than the ebonite rod. I will bring back the ebonite rod, and without charging it again, it has lost a little charge. Now it reads minus 5.7 kV, and the acrylic rod reads about plus 5.2 kV. Outside of the classroom, this meter has applications in various industries for detecting static charge buildup on various materials like carpet, paper, fiber, yarn, textile, and rubber, and used in various types of environments like electronics, laboratories, packaging, textile, printing, injection molding, and manufacturing. This meter identifies where the static charges are building up, how strong the charge is, and confirms if the anti-static measures are working. Electrostatic discharge, or ESD, is something to be avoided. For example, we use ESD-safe tools, anti-static mats on workbenches, Wrist straps. To explain why ESD is such a huge concern, if an electronic device receives a static discharge, it can either be destroyed and fail right away, costing the company a lot of money, or more worrisome, it is damaged, appearing to work, but will fail later or act unreliably. Another way to control static electricity is to use an ionizer. An ion generator will keep these charges neutralized and safe to work with sensitive electronic components, preventing electrostatic discharge before it happens. To change the meter's function to ion balance, first we must push the IB button. This has two effects. The red LEDs turn off and the scale is switched to V for volts. The other thing we must do is install the ion balance plate into the front of the sensor. This plate creates a surface where ions can be accumulated and measured. You are expected to measure the ions at a distance from the ionizer at 12 inches. It is important to note that when the meter is in this mode, it has a smaller range of -220 to +220 volts. If this is exceeded, there will be an alarm, and you must get the meter out of the field or risk damaging the meter. For demonstrations, I don't have a balanced ionizer, but instead I'll use this negative ion generator and measure its output. It's quite strong, and when I turn it up all the way, it will make the meter alarm, warning me that the meter can be damaged. The meter has two other buttons. The hold button will freeze the reading on the display until the hold button is pressed again. The 0 button will dull out the offset in the meter. There is a backlight function that is activated when you are first turning on the unit and hold the power switch down for a few seconds. The light will come on. However, this light is too dim to read the display in a darkened room. But since I don't plan to use the meter in the dark, that's not an issue. If you continue holding down the power button, the backlight will turn off and you will see the message A off on the LCD display. This indicates that the power auto shutoff is disabled. By default, this meter has a 5-minute automatic power shutoff to prevent draining the battery. The case of the meter is conductive, so the meter can have a ground reference when the meter is held by hand. But for a more accurate reading, the ground clip can be plugged into the meter and the alligator clip attached to a known ground source. Overall, this meter is an excellent value. It appears to be well constructed, and it will be useful for the projects that I am presently building. If you want to see what I'm using this meter for, I've made a separate video and posted it on my YouTube channel, Hobby Paranormal. The video is entitled DIY Making an E-Field Detector. Thanks for watching.